Okay, so last time, which was really Zach from last year on YouTube. Yeah.
You mentioned like the sliding window, like MPP or MPC
Yeah.
type running for the
For state estimation.
for state.
Yeah, sometimes called receding horizon estimator, sometimes called sliding window state estimator.
Well, I mean, like I feel like that's the same terminology as SLAM stuff for like.
I mean, SLAM is state estimation.
Well, is it
It's the same stuff. Yeah. So I mean, the classical algorithms for SLAM are Kalman filters and moving window, receding horizon. Yeah, it's the SLAM is really solving like a Bayesian inference problem. It's solving like essentially a state estimation problem. They are tightly coupled things. That, yeah. Sorry, was there more to that? I'm sorry if I cut you off.
No.
That's it. Yeah. Yes, they are the same thing. Yeah, I mean these things are very like everything's kind of the same set of ideas, and there's these things go by lots of different names and like different subfields and stuff. So I think the aerospace name is and also like the more classical name from like I think both chemical process engineering people and aerospace people call that like MPC dual thing, a receding horizon estimator. I think the SLAM robotics people call it a moving window estimator. It's the same thing. Okay, cool. And yeah, there's specific reasons that the SLAM people do it that way also, that are maybe interesting. Maybe we should talk about this if you want. So brief thing, right? So that stuff, the factor graph stuff is kind of where you're coming from. Yeah, so that's receding horizon estimator. The reason they do it that way is that in that context, the state vector, which in SLAM includes all of your features, can get huge. And then the covariance matrix over that is huge squared. So it's very, very inconvenient to represent that gigantic covariance matrix because the problems are too big. So instead of running a filter that needs a covariance matrix, they run what essentially is a trajectory optimization problem. It's a batch nonlinearly squares, but it basically looks like direct collocation and has all that nice sparsity, just like we talked about with collocation. And they have like all these really all of that like sort of factor graph stuff is about. The factor graph is literally the sparsity pattern of the resulting matrix in the KKT system. So that's what that thing gets you. And then they have all this stuff about, ordering and variable elimination and all. What that really comes down to is they do a sparse QR factorization. Like GT-SAM is literally just sparse QR, where they get the block sparsity from the factor graph. And it's a special QR factorization that exploits the sparsity coming from the factor graph. Does that make sense? So yeah, that's much, much more computationally efficient. This is a kind of a good example of like the trade-offs between sort of direct and indirect and blah, blah, blah. Like in our context, this would be like roughly speaking, a Kalman filter looks sort of like DDP, but it's dual, it's flipped around, right? And like the Kalman filter thing, it's a covariance, and DDP, it's a Costigo Hessian. Whereas collocation, that never shows up explicitly. Right? Instead, you have this big sparse thing, KKT system you factorize. So GT-SAM is sort of like collocation, and it's exploiting the sparsity. It never explicitly forms that covariance matrix, which in this context, the KKT system is super sparse, but the covariance would be dense if you tried to form it. And that's now huge in the SLAM context and computationally gnarly. So they avoid it by doing the moving horizon thing and by keeping that KKT system super sparse, which is what that factor graph stuff's all about. So there's multiple views on this stuff. Hopefully that was somewhat insightful. People in that community, in the factor graph, the people who are into factor graphs are really into factor graphs, and they've tried to port those ideas over to control in a bunch of papers in the last 5 years or so, most of which end up being, hey, look, I have all this factor graph sparsity stuff, and it's equivalent to Riccati. Is essentially the punchline on all those papers. Yeah. It's not. It's exactly the same. So literally all a factor graph is a way of understanding the sparsity of the resulting like matrix that you build in the nonlinearly squares solver. It's basically encoding the sparsity pattern, the block sparsity pattern of your like KKT matrix. So you can use it to write down the sort of sparse KKT matrix that shows up in control problems as well, and people have. So yeah, I mean, there's actually deep connections between graph theory and sparse matrices. There's like whole research areas in this. So like, if anyone's familiar with graph theory at all, you've heard of like graph Laplacians and things like this. Basically, what that comes down to is like, there's a graph for every graph, there's an equivalent matrix representation and vice versa. So like a lot of understanding, of the structure of sparse matrices. There's a lot of insight from like converting those into graph representations and understanding the graph. So factor graphs and sparse matrices they're just two sides of the same coin. And you can kind of view things either way. And I tend to be much more into the, like just sparse matrix numerical stuff. But like if you go talk to Michael Case, for example, he's like all about the factor graph stuff. And there's insights from both sides. Um, and they're both cool. But they end up at the end of the day basically being equivalent things. So it's whatever you like to, you know, use in your brain to think about it and understand it and visualize it. Whatever works for you is cool. But yeah, there's deep connections between graph theory and sparse matrices. Okay, that was fun. Thanks. Anybody else? Okay, cool. So that stuff is interesting. The duality between state estimation and control is like a cool thing that like I've gotten a lot of mileage out of and is worth knowing about and thinking about that I kind of teased. Okay, so that was kind of last time LQG sort of finishing up things, Kalman filter stuff, a little bit of that like duality conversation, which you just kind of had, right? By the way, yeah, like particle filters and PPI, same thing, right? Just one goes forward, one goes backwards. MPC is moving horizon, right? LQR is Kalman filter. These are all like essentially the same algorithms. And they're just kind of change the names on certain things, change the direction of time. They're basically the same thing though. Okay, so today we're gonna do some fun stuff. We're gonna talk about the rocket soft landing problem, which is A, just awesome, and B, this is like one of the seminal results from like, I'd say modern control of the last like decade. So the stuff we're going to talk about today, I'll like tease some stuff right now. We're essentially going to talk about this paper, which came out in 2013. And the authors are, first off, there's Bechet Achikmashe, who's now a professor at University of Washington. And then these two guys, so John Carson's still at NASA, and Lars Blackmore is now like a senior guy at SpaceX, like runs the GNC group at SpaceX, basically. At the time, all three of these guys were at JPL. So we're all at NASA at the time. And this paper, again, like huge deal, seminal result from 2013, basically shows you how to take the non-convex, very non-convex problem of landing a rocket and magically convexify it such that it turns out to be a convex MPC problem that you can solve now online, really fast, super reliably with all the guarantees and all that kind of stuff. And this really opened the door to SpaceX landing rockets on barges and the powered descent stuff for landing on Mars. This is kind of like the theoretical, like this paper kind of led to all that stuff, which is really awesome. So just to get you psyched up, we're going to now do some YouTube exploration. But check the paper out. The paper's a modern classic, now like 11 years old, whatever. So this is like now a couple of years old, but this is, Starship doing the thing from a couple of years ago. We'll fast forward a bit. So yeah, all this stuff, cool, whatever. But the landing part is the part we want to see. This is a test flight they did, right? Yeah, it seems reasonable. So here we go. So this is powered descent, which is what this rocket soft landing is all about. And everyone's kind of seen these things at this point, but it's still cool. So landing on the pad kind of thing. So there's Starship. This one's like 3 years old. Here's a more recent one that's maybe cooler, which is the chopstick thing. Who's seen this? Yeah, super sick. So okay, so this is the last one was the upper stage of Starship, right? This is the booster, the lower stage. And what they're doing now is they're landing the first stage, and then instead of landing it on a pad with legs, they catch it with this gantry from, which is just insane and awesome. So that's kind of telling you how good this is, right? That's how accurate this is, which is wild, right? They're getting it within like a couple meters maybe, such that they can like grab onto it with this thing. It's pretty nuts how good it is. And again, SpaceX, Lars Blackmore, third author on the paper. So yeah, pretty nuts. Like the level of, control of to get that to happen is pretty wild, right? It's really, really good. Okay, so that's the SpaceX stuff. And then the other end of this is Mars EDL. So this is Perseverance, Mars 2020. This is now like from 4 years ago. This is the animation of this thing. So this thing, maybe we'll back up a little bit. I'll narrate. So we actually worked on this stuff. This was one of the first projects I worked on. I got a NASA early career award my first year as a professor, and we did a bunch of stuff on Mars entry, descent, landing. And so kind of interesting. So the gist here, maybe I'll go through the whole thing and we'll like narrate a bit. So this thing's coming in on an interplanetary trajectory. Just some context and like what this all looks like. When it gets to Mars, all of its navigation information comes from Earth, from the Deep Space Network. The position uncertainties are about 1 kilometer when it gets to the Martian atmosphere. And the uncertainty in the Martian atmosphere is huge. It's like you don't really know what the atmospheric density is. You don't know what the winds are, all this kind of stuff. So there's very, very large uncertainties in here, which is why this is kind of hard. And doing like pinpoint landing is very hard. So this is where you have atmospheric interface. This is like fireball. You're dissipating all your kinetic energy in the atmosphere at this phase. And then once you're kind of out of the fireball situation, the parachute's going to deploy. This is also really hard, it turns out, because Mars' atmosphere is very thin compared to Earth. So the capsule is actually still going supersonic when the parachute pops out. So figuring out how to deploy a parachute like this in supersonic flow is a huge challenge. They did a ton of like really high fidelity sim work and then tried to validate this in a wind tunnel on Earth, but no one was totally sure how it was going to work. And then at this point, yeah, you're a few kilometers off from where maybe you want to land. The aeroshell drops off, and now they have cameras, and this is terrain relative navigation now, where they're using cameras to figure out where they are relative to features on the ground. That TRN stuff was developed at CMU, and most of the vision people at JPL who did this are CMU alumni, which is pretty cool. Then this is the power descent phase. So this is the stuff, the control problem we're talking about today. This is the sky crane, right? So now this it's got vision on board. It's trying to avoid boulders and find a good landing spot. And then it's going to hover a few meters up, and they're going to drop the rover off with a crane. And then that's this part. And then once the rover touches down, they cut the cables, and then the sky crane vehicle, this thing is going to basically fly off a few hundred meters so that they're very sure that it's not going to be in the way or damage anything, and then just crash. And that's it. That's how that works. Kind of cool. The part we worked on that we wrote a bunch of papers on is the entry guidance phase. So that's the fireball part. It turns out you can steer in the fireball phase to try to reduce your error, but you don't have any state estimation. So the tricky part there is you have about 1 kilometer uncertainty when you hit the atmosphere, huge uncertainty in the atmosphere, and you're just dead reckoning with your IMU. That's all you've got. And the way you steer is, so the vehicle is, the center of mass is slightly biased off of the center of pressure. So you can think about it as like kind of lean back a little bit, and that generates a lift vector. And the classic way of doing this is called bank angle guidance. It was developed during the Apollo, for the Apollo missions, and it's still more or less what's used now. So you have this lift vector, and you have drag, obviously, and you can, they call it bank angle, but I would call it yaw. Basically, you can rotate the capsule around. You saw the thrusters on the backside. So you can use those to kind of basically steer it like this and steer the lift vector. And so obviously you can control your cross track direction like that. What if you're going too long and you need to shorten up the landing spot? So what they do then is you basically zigzag to bleed off. So that it's kind of a really weird, complicated algorithm, but basically it has this phase where it's only controlling the along track distance by zigzagging for a while. And then in the later phase, it only controls cross track. And then the parachute opens, and that's the end of it. That's called bank angle guidance. Again, Apollo era stuff. We worked on doing stuff better than that using convex MPC ideas. But that's kind of how it's done. Any questions about that? It's kind of fun. So that was the animation. Now we can watch the real thing. It's cool. So this is real video that was coming in live during the landing. So this is after the parachute opened up. This is like the TRN camera looking down. And I think you can hear some stuff.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. The confirmation that the backshell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here on 50 Bravo.
Pretty sure
yeah.
that voice is my
Completed
buddy.
our terrain relative
Started up in
navigation.
undergrad.
Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity
And then you can see-
accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started. About 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars. Ready to begin seeking the sands of past life.
Okay, awesome stuff. So now we're going to kind of walk through this. I'm going to give you like the really high level kind of view of like how the whole stack works and then what this paper's about. I'll give you like the key nugget from this paper and then you can go check it out for yourself later. Any questions before we get into it? All right. Yeah, it's the same basic kind of this powered descent thing. It's the control problem is called the rocket soft landing. It's one of these classic control problems, like benchmark problems that's been around forever. And basically this major sort of contribution from this 2013 paper was a convex formulation of that problem that was like practical. So you could actually do it on board.
Why did big SpaceX rocket landing? Like I'm not sure that the timeline is SpaceX did rocket landings on Earth after the Perseverance soft landing on Mars.
No, these things are all kind of happening around the same time, I would say. Like people were working on this stuff. So the Blackmore Betchett paper that I showed you, that paper was written while all of those guys were working at NASA. And then like all of the stuff I showed you, like the Perseverance landing was 2021. SpaceX stuff was happening all kind of, you know, around that same time, like, you know, 2010s, you know, kind of. So yeah, it was all kind of around the same time. And I think this paper was kind of like a big enabler for a lot of these things. Yeah. Yeah, there were a bunch of things. So in particular, Perseverance was the first to use TRN, to use the vision-based terrain relative navigation stuff. That was the new thing. Prior to that, they didn't really do TRN, and the error ellipsoids on the landing were a lot bigger. I think that's the biggest one. Otherwise, they were very, very similar. Yeah, so for context, the error ellipsoid projected on the surface of Mars, like the landing sort of miss error for these is like 10 kilometers-ish. And so I think the nominal sort of ellipsoid, I think for this one was like 8 by 12 kilometers or something, and the prior one was more like 20. So like they got it down by a factor of 2. But yeah, it's quite large. And to be clear, the TRN stuff is not, they're not using it to get to a desired landing spot. They're basically using it because they don't have enough fuel for that. So, you know, if they're 5 kilometers away, they're not going to fly 5 kilometers with the sky crane. They're basically looking to find a flat spot where there's no big obstacles, where they can safely touch down near wherever they are. Okay. Yeah.
So when the rover's entering Mars' atmosphere, how do you know its orientation relative to the surface?
IMU.
Just that.
Yeah. Yeah, basically it's all dead reckoning with an IMU most of the way down. And then once they pop the back shell off, the air shell off, then they're using the cameras to do some localization. But it's basically vision and IMU. Okay, so let's get some stuff going here. So first thing talk about is like kind of what this problem looks like and kind of how it fits into the full stack. Okay, so first, the problem, like this is kind of this mathematical idealization, right? It's kind of the classic control problem. So the idea is you want to go from some initial state x naught that is presumably somewhere off the surface, you know, falling ballistically or something like that, to some final position, call it R final, with the height equal to 0 and the velocity approximately 0. So that's the so landing implies that the final height is 0, and soft implies that that final velocity is 0. Like that's basically what that comes down to. And usually, so these are basically constraints, right? And then usually the cost function involved here is some combination of fuel. You want to minimize fuel consumption and or landing position error. So you want to hit some desired target. And there's sort of different variations on the problem. So minimize some combination of fuel consumption and or landing error, like position error. So something like, you know, like R final minus like R goal or something like this. And then also in addition to this, you have to respect various other constraints. So the common things are thrust limits, which we'll talk a lot about. That's kind of the main one that's non-convex that makes this tricky. And that's where the magic of that paper comes in. So you have thrust limits and usually also safety constraints. So the common safety constraints are, so it turns out if you set this problem up naively and just hit go, the fuel optimal trajectories will go through the ground and come back up on this like parabolic arc. So obviously that's bad. And so what's commonly done is, from a safety constraint perspective, is to enforce what's called a glide slope constraint. So it basically ends up looking like a cone. So you want the rocket to stay above this cone that kind of funnels you into the landing site and sort of stay high off the ground until you're really close to the landing site is the idea. So glide slope constraint is kind of a standard safety constraint. Okay, so some examples that we just checked out would be, so first, also for some like, yeah. Oh, that's super weird. My mouse is on my iPad, not on my computer. How did that happen? I really don't know. Well, now I can't scroll my, that's super weird. Does anyone know? What the hell? Oh, there, okay, now it's there. Okay, that was really weird. Never seen that before. Okay, anyway, so we got, on the NASA side, we just kind of saw some, so the first kind of NASA mission that did this was the Curiosity Sky Crane, which that was first done in 2012. And then SpaceX started doing this stuff with the Falcon. And then Starship. And you've all seen that by now, right? That's been kind of going on now for like 10-ish years. And then the one we just saw was NASA Perseverance, which added this terrain relative navigation piece, the vision piece to it. And that was in 2021. Okay, so that's some examples of where this stuff is used. And now to kind of like give you a little bit of like kind of the lay of the land and what the full stack looks like for something like this. So a big kind of picture thing here, which is common in a lot of different areas. You'll see similar control architectures in, for example, drones. If anyone's done any drone stuff with like Pixoc, PX4 stuff, it's very common to have a hierarchical control setup where you have a position controller on top that maybe runs slower, and then a faster attitude controller that's like underneath that. And you have these kind of two separate loops. This is also common for this rocket landing stuff. So we're going to have a state that's got a position and velocity here for the vehicle. And then generally speaking, you're going to have a position controller. And this is actually the part we're going to talk about that is kind of the piece that gets solved with MPC. And that position controller is going to spit out as output a linear acceleration command that it wants the rocket to follow. And the way the rocket follows the linear acceleration command is by gimbaling the rocket engine and by the attitude controller. Essentially, if I want to go this way, the lower level controller basically needs to tilt the rocket over to fly that way, right? So that's how this ends up happening. So the position controller is basically reasoning about point mass dynamics at like an F equals ma level with a bunch of constraints on it. And then it sends acceleration commands to an attitude controller that then turns those into kind of thrust angle commands, thrust and gimbal angle commands. So these we'll call T and theta. And those get run on the rocket. And then we'll have some kind of state estimator. And this thing is going to provide into the attitude controller kind of a quaternion and an angular rate. And then to the position controller, it's going to provide the position velocity, right? So maybe I'll go label some of this stuff. So obviously this is position velocity. This is acceleration command. Linear acceleration or translational acceleration. And then this is thrust and gimbal angle. And then this is attitude and angular rate. Okay, questions about this? This is like the overall setup. And this, yeah, again, this like hierarchical kind of position and attitude controller getting decoupled like this is kind of standard in a lot of different applications, in particular drones. If you've ever done any of that stuff, you'll see this kind of similar idea. And then just a quick word about like what the state estimation stuff looks like here. So for the SpaceX case, it's basically just GPS. Those landing things, these are terrestrial scenarios. You have GPS, and the GPS receivers, if you use like high-end stuff, you're just basically just fusing GPS with an IMU. That can get quite good, actually. Like you can get very, very good velocities out of those. And if you design the GPS receiver and you do the inertial fusion with a good IMU well, you can get down to kind of meter level positions pretty easily, even better if you're really good. So it's really just GPS and IMU and all that stuff. That's kind of all you need with good filtering. Gets you to maybe like 1 meter position accuracy. And then on the velocities, you can get to like better than 1 centimeter per second accuracy. And then, yeah, attitude, you can get to like 1 degree accuracy. So basically for this problem, GPS and an IMU are kind of all you need, is the message. For the Mars landing case, we obviously do not have GPS, and that makes this a lot harder. So in that case, they've got the IMU, which during the kind of fireball entry phase, that's all you have. You have no other sensors. There's a radar altimeter that's telling you how high you are above the ground, which is obviously really important. So you want to know that really well. And then now with the TRN stuff, you've also got the vision system. And this gets you to about maybe 30 meters. But again, you're not really trying to fly to a pinpoint landing because you're like 10 kilometers off by the time you sort of pop the parachute because of the initial uncertainty being about a kilometer when you hit the atmosphere and then dead reckoning through the atmosphere with your IMU. By the time the parachute pops, you're kilometers off. The power descent phase doesn't happen until you're like pretty low and you don't have enough fuel to do like a 5-kilometer traverse with that thing. So you're really at this stage just looking to avoid boulders and find a good like flat landing spot. NASA's goal for the next, I don't know, few years, potentially leading up to human Mars landings, is to get the landing air down to 50 meters. They want to do like precision landing, which again, really hard. One of the things that we've been thinking about and others have been thinking about is to really get there reliably. What you really need is a Martian GPS system. There's various ways you might do that, but having like a bunch of satellites in Mars orbit that can really nail down your position accuracy in real time would be a good way of doing this.
Do they use radar velocity as well?
I mean, yeah, that radar altimeter absolutely can give you velocity information, normal to the ground as well. Yeah.
For the IMU in the Mars case, is it all just relative movements? Are they actually tracking like Mars's gravitational field for an absolute measurement? Or...
You really can't get absolute measurements, period, out of an IMU. Like they're measuring linear acceleration and angular velocity. So like linear acceleration, the gravity vector shows up in there. But you're not really getting like absolute anything out of this.
You have some idea, I guess, when you first enter that you can then kind of...
You basically take your initial conditions from orbit and then propagate from there. Yeah, just integrating the IMU, dead reckoning. And I mean, these are really good IMUs. These are like super, super high end, like fiber optic gyros, et cetera. So they're, you're integrating this for several minutes during that fireball phase. At the end of that, you might be a couple degrees off in attitude, but the position errors, they started out being like a kilometer. And at this point, they're probably, several kilometers, around 10-ish maybe. And that's just the nature of the beast. Anybody else?
Position accuracy much worse than altitude accuracy?
Well, it depends on what you mean there. I wouldn't say it's better or worse. They're completely different things with different units, so it's hard to compare. Generally speaking, on a spacecraft, you can know your attitude really, really well from star trackers, for instance. So like spacecraft attitude determination is very, very well understood. And like the state-of-the-art thing would be to use star trackers. So for sure, the vehicle flying to Mars knows its attitude super well from star trackers. Position's much harder. So it turns out like state-of-the-art for navigating to Mars, for instance, is to use the Deep Space Network, which is this series of dishes on the Earth. And to do, there's various techniques. The kind of state-of-the-art stuff is called delta doors. It's basically measuring the difference in time of arrival from signals at 2 different dishes on like opposite sides of the Earth. But essentially all you're getting out of this is you're getting some angle information from that. You're getting a range measurement and you're getting a range rate measurement. So you can basically measure range, the velocity component along that range direction from Doppler, and then some kind of angular information from this delta comparison, but that's quite bad. So at the end of the day, you're doing filtering over very long periods of time. So like to first order, let's just say you have range and range rate. It's basically giving you like one component of the position and one component of the velocity, right? To get the full 3D position and velocity, effectively what you have to do is wait for the motion of the spacecraft and the motion of the planets to put you in different positions so that you're measuring a different component of the position and velocity in like inertial coordinates. Does that make sense? So you're measuring these things over time, and then you're relying on the dynamics model to kind of propagate those components through time in between those. And so as a result, the position accuracy you can achieve is highly dependent on the quality of your dynamics model and all the quality of the measurements and stuff. So it's pretty tough. So kind of state of the art again, like by the time that thing gets to Mars, it's about a kilometer when you hit the atmosphere. And that's quite That's quite good, actually, if you think about what's going on there. But it's nowhere near what a GPS-like system could do, right? Cool. Okay, any other questions about this? All right, so let's see. Then like about the control loop. So there's this high-level position controller. This thing uses a point mass model. And it's just F equals MA. And it's reasoning about for safety stuff, thrust limits, and fuel. And this thing is generating linear acceleration commands. And runs at, say, hertz. So this might run at like 5 hertz, 10 hertz, something like that. And by the way, this is a very common sort of architecture, right? I mentioned drones. This sort of setup, though, is also extremely similar to what the classical like quadruped MPC controllers from like Cheetah look like, if you know how these work. Like, so it's these things are quite closely related. And then you have this low-level attitude controller. And this thing is reasoning about your attitude, also flexible dynamics of the rocket. It turns out rockets are actually flexible at the sort of like hertz level. Like the lowest bending mode on a rocket can be like a couple hertz. So they're not that stiff, and you actually have to think about this hard in the controller to not shake the rocket apart. Then you've got also fluid slosh. And then this thing is generating thrust and gimbal commands for the engine. Ultimately to track the desired acceleration coming from that higher level controller. And this thing is running maybe an order of magnitude faster than that position loop. This might be running at like, tens of hertz, typically. Okay, any questions about this?
Burning fuel mass is going, right? So does it affect the mass?
Yes, very much so. So we're about to talk about this right now. So next up is rocket dynamics and like what the models of this looks like. So yeah, you're 100% right. In fact, the fuel mass is the dominant mass of the system. Like the fuel weighs more than the rocket in rockets usually in a launch vehicle. It's kind of wild to think about. So yeah, when we talk about it's not actually F equals MA because the M is time varying. So it's actually F equals dp dt, where P is the momentum. And it's, you've got an M dot term in there basically, right? So it's if remember, force is the derivative of momentum, right? So it's really F equals M dot V plus M V dot. That's really what's going on, right? And yeah, you have that very much in this case. So that's one area. This is a little different. So here's our little cartoon rocket. We've got a thrust. So we have an engine down here. We have a thrust vector, T, and you can steer that to some degree, right? The rocket engine is gimbaled. So you can tilt the rocket engine and tilt that thrust vector. We've got a center of mass somewhere over here. And then you've got this length between the center of mass and the engine, which we'll call L. And then inside the rocket, you also have a bunch of fuel and it sloshes around a bunch. So a standard model for this is actually having like a pendulum inside the rocket to model that fluid sloshing around. So let's see, what can we say about this? So we've got, we'll model this as a rigid body, but it's not, right? But that's kind of standard model. So you might have like sort of some F-Lame stuff. So we've got, gravity, and then we'll have thrust over mass. So this is just point mass dynamics. And then we've also got the fuel burn dynamics. So that looks like this. It's where you've got, it's some like coefficient times the thrust, basically. So this would be point mass dynamics and fuel burn. So these two things are what's in that high level controller, which we're going to talk about here. And then you have, so these two things go in the position controller and are sort of slow in the slower loop. And then we also have the attitude dynamics. So this is Euler's equation, which we've now seen a couple times for like drone kind of stuff. And then this is L, which is the distance from the CG to the thruster, cross T, right? That gives us the torque. And these are the attitude dynamics. And this is torque applied by the engine. This is the inertia, right? You've seen this kind of stuff before. And this is the attitude controller, which we're not going to explicitly talk about, but in principle, you guys kind of know. You've seen this sort of thing before for like drones, right? Okay, so this is some stuff about this. For a launch vehicle, the fuel can be like 80% of the or more of the initial full system mass. So like you have to think about that fuel mass in this case. Which is why we have that second equation there with the m dot. And then kind of the big thing where this shows up. So in addition to just it changes the mass dynamically as the thing's flying. Another big thing is fluid slosh. So you have this fluid, which again, the level of the fluid's changing a lot, but it's a huge portion of the overall mass and it's a liquid in a tank. So as you move the rocket around, that fluid is sloshing back and forth in the tank. And this can do very bad things if you don't think about it. So first of all, it's highly nonlinear and it's hard to model. And it's time varying. So there are standard models and people do try to people actually do experiments to try to calibrate models here and do like gray box models. Again, the standard one is like a pendulum inside the rocket. But obviously that's not very accurate and there's, but you can, like, for example, you can model a pendulum inside the rocket and you can fit the length and the mass of the pendulum to data and try to go that route. That's like a pretty standard move. But ultimately, what ends up happening here is you try to do something like that, and then you use robust control techniques to try to sort of bound the badness and make sure that the controller will still be stable and not crash in spite of whatever inaccuracies that model has. Yeah.
Exactly your conclusion, but has there been attempts to use the fuel that maybe is that's more viscous or like in a more solid state to avoid this?
So there are solid rockets. But there's a bunch of trade-offs there. So there's a bunch of different rocket fuels. It's usually not done for this purpose, but you're right. So there are various liquid fuels that are usually a mixture of an oxidizer. Like so SpaceX, it's kerosene. It's basically jet fuel and liquid oxygen, kerosene and liquid oxygen. That's pretty normal. There are weirder hybrid things. So actually paraffin wax can be used with an oxidizer as a fuel. And then there are solid fuels. The problem with the solid fuels is that they're not throttleable. So generally speaking, with a solid rocket, you light it and that's it. It's going to go till it burns out. And you can't really throttle it down or turn it off. Whereas a liquid fueled engine can be throttled up and down and turned off and on. So this is the main trade-off. Let's see. Okay, other things to say. Okay, there's flexible modes. These things are floppy. So rockets are built to be really light. And as a result, their mass is obviously at a huge premium. So that means that they're kind of inherently not very stiff, or they're basically, there's a trade-off between mass and stiffness. So you really prioritize being light. And as a result, you're kind of constantly playing this game of like, how light can we make it? And you make it just heavy enough with just enough structure so that it's just stiff enough. So as a result, there's always kind of low frequency bending modes. And in robotics, we tend to, not have to think about this stuff because we can, for terrestrial applications, we can build things that are heavy and kind of get away with it. But for these applications, you're basically always reasoning about flexible stuff somewhere. And for a rocket like this, typical first bending modes are single-digit hertz. So they're absolutely inside the bandwidth of your controller, which means that your controller can excite those modes, which means you can very, very easily end up in a positive feedback loop where if you have a controller that's, so if the rocket bends and that causes some error, the controller is going to counteract that. And it ends up that you can end up basically pumping energy into the system from that at exactly the modal frequency. And you end up with this positive feedback loop and it blows up and it ends up shaking the rocket apart. This actually happened in the early days of the US and Russian space programs in the 50s and 60s, where the stabilizing controllers were literally exciting low frequency modes and the rockets were blowing up shortly after leaving the pad because they got shaken apart by their own control systems. So that's bad. Yeah, so first modes are typically in the hertz range. And the standard kind of old school approach to this is in the frequency domain, you add notch filters to the controller at the modal frequencies. So you basically do some, vibration testing, whatever or CAD modeling, and you know where those modes are. And any modes that are inside the controller bandwidth, you add a really strong notch filter into your controller at those frequencies so that it doesn't put any energy into those frequencies. That's an old school way of doing it. A new school way, like if you wanted to do it with a linear state space model like LQR, is you would actually model the bending mode in your A matrix. And then you would put so you can add a mode is a degree of freedom, right? So that means it's got a state with a modal coordinate state and a velocity, right? So it adds two states to your state vector, and you can there's a whole literature on this, right? But it fits into like your manipulator dynamics. So you would model that in your dynamics and you'd have an explicit set of states associated with each mode. And then you can just put heavy penalties on those guys in the controller in your like Q matrix such that the controller won't excite those, right? So that would be like the kind of model-based way to do it. But the kind of more standard old school thing is putting in notch filters to the low-level attitude controller. At those bending frequencies. To avoid shaking your thing apart. And then other stuff that's not modeled here would be aerodynamic forces, quite obviously. And it turns out that for these purposes, we mostly ignore them. By the time you're doing this power descent stuff, the vehicle's not moving that fast, and the aerodynamic forces are kind of in the noise. And you can kind of make sure, because you can kind of make sure that these are small by having velocity constraints in the position controller to kind of make sure. So you don't want to be flying that fast. And remember that aerodynamic forces are proportional to velocity squared. So V small, V squared is really small. And then these things kind of don't matter that much. And then basically in all of these, so all the stuff I just wrote down, right? Fluid slosh, flexible modes, aerodynamics. These are all things that we're kind of not modeling, or we're doing a really crap job of modeling, and they're highly uncertain and time varying. And so what ends up happening here is there's always lots of model uncertainty. And what is standard practice in this game is to use linear robust control ideas to try to bound these errors in the models. Design controllers that are super robust across a broad range of possible modeling error to make sure that the rocket doesn't blow up on you. Sorry. And that's all showing up in the attitude controller, in that low-level controller. Okay, cool. So that's kind of high-level stuff. Now, anybody else before we move on? Cool.
Your rocket that makes state estimators to kind of map out your fluid slosh and.
No, not really. You're not really measuring it. It's kind of unobservable in some sense. It shows up obviously in like your IMU data and things like this, but it's not explicitly modeled or, measured or anything. Okay, so now we're going to zoom into that position controller and talk about like kind of this convex relaxation idea and like what's going on with this paper, and start out with, hopefully I can actually talk. What this whole convex relaxation idea is. So everyone remember convex sets? So when we talked about this, and we talked about like QPUs and stuff. So a convex set is one where you can take any 2 points in the set and draw a line between them, and the line is completely contained in the set for like any 2 points, right? That's definition. So sometimes we'll have a non-convex constraint. And so to be clear, convex relaxation's a huge area with lots of different stuff. I'm showing you like the particular flavor of convex relaxation that is used in this paper that shows up in this soft rocket landing application. That's kind of cool. But yeah, so the gist is sometimes you'll have a non-convex constraint that can be written as the boundary of a convex set. So I'll make this hopefully concrete. So good example would be a like a sphere. So if I have a constraint that says, X has to be on the sphere, so we'll call this S1. So this is the original set. Where S1 is set of X's such that norm of X equals 1. So it's on the unit sphere, right? So that's non-convex. If I pick 2 X's that are on that sphere, I draw a line across. The line's not on the surface of the sphere, it's in the interior. But if I enlarge this set to what we'll call S2, where I include the inside of this sphere, so that's a ball now, and this, we'll call this S2. So this enlarged set, and this thing is S2, which is all the X's such that norm of X is less than or equal to 1. So basically include the interior now. That's a convex set, right? We know that. And in particular here we have, in fancy notation, S1 is the boundary of S2, right? So the idea is I have some constraint, like a norm constraint. Norm of X has to equal 1, non-convex. But if I enlarge that by turning that into an inequality, include the interior, now it's a convex set. The new set is strictly bigger than the original one. So that's why it's called a relaxation, right? I'm relaxing it. I'm making the set bigger. So the idea though is, if I go solve any optimization problem, I can always do this relaxation, but the solution to the problem of the relaxed problem might be in the interior there and might not correspond to a valid solution of the original problem, right? So the relaxed problem is actually strictly easier, right? So I might get a solution to the relaxed problem that's not a valid solution to the original problem. It'll maybe have a lower objective value, whatever. But this idea of replacing the original non-convex constraint with the relaxed one, the bigger one, is called convex relaxation. The convex relaxation. And there's lots of different kinds of convex relaxation. This is just one example, but they all kind of have this flavor of you take whatever original thing you had, it's all messy and weird, and you sort of basically enlarge it into a bigger convex set. A really classic one, the good one, is when the original set is already is the boundary of a convex set. You just include the interior. That's the one we're going to do today. Okay, so that's step one. The other piece of the puzzle here, which ends up showing up in this rocket landing problem and sometimes shows up in problems when you're really lucky, is if you have a particular kind of cost function, you can get really lucky and have, if you have the right flavor of cost function, you can prove that the cost function's always going to push the solution up to the boundary. So even though I enlarge the set to include, like here, right, the interior, if I have the right sort of cost function, the optimum of the relaxed problem is always going to lie on the boundary of the set anyway, because of the type of cost function, which means that even if I solve the relaxed problem, my solution's always going to be the true solution to the original problem. If that happens, that's you say that the relaxation is tight. And so can anyone think of a cost function that would do that for you off the top of your head? But that's a non-convex objective. Think about a convex objective that would do this. Yes, perfect. So if you have a linear cost function like C transpose X, what that's telling you is to just go in the minus C, the minus gradient direction forever until you slam into a constraint, right? So in this case, what that's going to do for you is you're always going to end up on the boundary of the sphere in the minus C direction, like opposite that's perfect. So let's write that down. So if the cost is nice, you can still sort of recover the answer to the original problem. By solving this relaxed problem. So really good example, which you just said, is let's minimize a linear objective, C transpose X, subject to norm of X equals 1. So that's non-convex because of the norm constraint. But, and to draw it right, so here's our sphere. And then let's say C looks like this. So we know, right, the optimum is going to be to go along the minus C direction until we hit the constraint. And so this is X star. And just from like some cartoons and thinking about it for a sec, we know we'll get the same answer if we were to relax this into norm X less than equal to 1 instead of equal to 1. Because it doesn't matter because of the objective, I'm always going to end up on the boundary anyway. Does everyone see that? So this is a problem, just a toy example, a problem that has a tight relaxation where we still get the answer we want. So when this happens, we call it a tight relaxation. And there's like huge sort of theory of convex relaxations generally in optimization. There's all kinds of other more sophisticated versions of this. This is like the simplest kind of version of it, which turns out is all we need for this problem. Okay, anybody? So far, so good? Okay, so moving on. So let's talk about the rocket problem and where this shows up. So in this problem, we have a thrust constraint. And let's see what that looks like. So first of all, we have maximum thrust constraint, which is no problem. So that looks like, so if I have a thrust vector in R3, the constraint is just that norm of the thrust has to be less than or equal to some T max. So that's fine. That's the kind of thing we just saw. It's a ball. So I'm not super great at drawing, but I'll give it a shot. Something like this, right? And then basically T has to live inside here. And that seems fine. So that's convex, right? We all know that's convex. Cool. We just talked about that. Okay, so the next constraint we have is a thrust angle constraint. And this is coming from, I guess I should move this down a little bit. This is coming from the gimbal limits of the thrusters, right? So if you have this big engine, it's on gimbals so that you can tilt the engine, and there's just limits, there's hard stops on how far that thing can move. There's joint angle limits, basically. And this, we can write this down a couple different ways. The nicest way to write it down would be, so if I have some nominal, like, I guess, I don't know, normal vector, or call it like axial vector, whatever, the vector down the middle of the rocket. We'll call that n. If I take that thing's dot product with the thrust vector t and the normalized thrust vector, so the unit vector, this thing has to be less than or equal to cos theta max, where that cos theta max, that's a constant, right? Theta max is a constant. So that cosine, so this is a linear thing, to be clear, right? That's the main thing I want to get across. So that's like a nice way to write this down. And this is a cone, and it looks kind of like this. So I have this n vector defining kind of the axis of the cone, and then t has to be inside this cone. Cool. And then we already know, and then yeah, the angle of the cone down here is going to be, this is our theta max. Cool. So we've seen this already too, right? So cones are convex, right? We saw this when we talked about SOCPs and all that good stuff. So this is convex. So far, so good. So the last one, which is the problematic one, is that it turns out rocket engines, we talked a little bit about liquid fuel versus solid fuel kind of stuff. So this is a liquid fuel engine. It can be throttled, but it turns out liquid fuel engines can't be throttled super deep. They have also a minimum thrust constraint. So basically they have a big kind of deadband where it's either on or off, and they can usually only be throttled up plus or minus like 20%, something like that. So they have a minimum thrust before which you've got to just turn it off. So if we write that down, this looks like have my norm of my thrust vector has to be less than or equal to T max, which we already have. It also has to be greater than or equal to some T min. And if I were to plot that, I'm just going to draw this in 2D. It looks like a donut in 2D. And in 3D, obviously this is like a sphere with like a cutout in the middle, like a spherical shell with a hole in the middle. And if I think about this set, is this a convex set? Big no, right? I got the hole in the middle, so this is not convex. So this ends up being the problematic constraint. Okay, so here's now the magic trick, which is the crux of the paper, which I feel like in the paper, you're gonna have to like think about it a little bit. I'm gonna give it to you like, I think it's super clear written this way, which is like the Zach version, I guess. But if you read the paper, you'll be able to parse through it yourself. Okay, so the trick is we're gonna add a slack variable. Have we talked about this before? I don't know what a slack variable is. Slack variable means I just add an extra variable into my optimization problem and set it equal to some stuff. Gonna make the problem a little bigger. That's like an optimization lingo thing. So we're gonna add a new slack variable. And we're going to follow the notation of the paper and call this thing capital, is that a gamma? Capital gamma. So this is a scalar that's equal to the thrust magnitude. Okay, so here we go. So now I'm going to write down all the constraints. So first, we have this new variable. We're going to set it equal to norm of t. That's constraint number one. Now we're going to write the other one. So now we've got t min less than equal to. Now this is, instead of norm of t, we're going to put the gammas in. So everywhere there was a norm of t before, we're going to put the gammas in. So that's number two. Number three is going to be our thrust cone. So I'm just rewriting. So this is just the three things we had before, right? I just rewrote it now with the gamma in there. So let's take a look at this. So these two, they were convex. They're still convex. That's all good. Right? So the number two is just a linear inequality. That's completely fine. The third one is a cone. It was a cone before. It's fine. What about the first one now? What's that one look like? It's the boundary of a sphere now, right? So gamma is the boundary of a sphere. And I just showed you what, there was a little foreshadowing in this one. So now you kind of know what we're going to do. This one's the boundary of a convex set. It's the sphere. And we're going to play exactly the trick that I just kind of showed you or walked you through. So now we can convexify the problem. By doing that relaxation trick. We're just going to relax one. So now we're going to call this, I guess, 1 star. And all we're going to do is literally take that thing we had before and then make it less than equal to gamma instead of equal to. Then we've got the rest of it stays the same. Okay, so that's pretty much it. You do this trick, and now the question is, how do I know this gives me the right answer? So it turns out, basically, and the crux of the paper, which I'm not going to do in class, is they basically do this trick, and then they prove that the relaxation is tight for a couple of choices of cost function, in particular for a minimum error sort of choice and for like a minimum fuel choice. That paper that I showed you is like the first one. They had a series of papers that kind of built on this and took it in a few different directions and added tweaks and stuff. But basically the crux of the paper is play this game, and then they have a proof in the paper using Pontryagin's minimum principle that for some choices of the cost function that this relaxation is tight and will give you the exact answer to the original problem. And then you can land a rocket on, a barge or a spaceship on Mars. Pretty awesome. Okay, so I'll write that down. The paper proves that this relaxation thing is tight using Pontryagin's minimum principle, which goes way back to the beginning of the class. Okay, any questions about this? Anything else? Yeah.
You've got high level, but just theoretically, like you had some sort of supercomputer. I guess the main reason to set up this controller is the update speed. Like if you had something that could solve the whole problem at the first level, would you?
Yeah, so I think there's sort of a few things in there, right? One is, so yeah, 100%. If you had more compute to throw at this, you could maybe what the first thing you would do is like not do the decoupling up here, right? And like instead have the full, attitude and position control thing coupled together in one controller. I think that would probably be the next move. But there you'd still have to make some, so there's that part, which is like, think about compute limits and think about the size of the problem. There's another piece of it though, which is the convexity piece. And the reason why you still maybe want to do this, even if you had a lot of compute, is if you're doing this on board, online, and you're trying to like land a rocket, this is like a super high stakes, kind of safety critical scenario where you don't want to mess up. And if you just wrote the whole thing down with all the nonlinear dynamics, even if you had infinite compute to solve that thing, if you have a non-convex problem, in general, you can't guarantee that you're going to get the answer, right? It's really easy to like get an infeasible problem instance or converge to a bad local optima, this kind of stuff. And if it's an online real-time application, you really, really want that problem to be convex because you really want to be able to guarantee that your solver is going to converge, within 10 milliseconds or whatever, and give you the answer that you can stick on the actuators. So there's kind of two pieces. It's both a compute thing and a guarantee thing. And sort of, so I'd say like from a compute perspective, the thing that like we've kind of gotten a little into that I think is kind of cool is like, from this kind of angle, if I have a lot of compute, like if I have a GPU, I can solve a massive convex problem, which means I can have really, really huge linear models, which can include all kinds of weird stuff. So I can include flexible modes. I could do all kinds of weird things, right? I could do like Koopman kind of things where I do like liftings or embeddings, and capture a lot of like weird nonlinear effects, but I can still make sure that my problem's convex. And I can solve a giant convex problem with like a 10,000 dimensional state vector if I wanted to, by throwing more compute at it. But I still want to keep it convex so that I can guarantee you that I can hand you a good answer in 10 milliseconds, right? So I don't know, there's sort of two things going on there. Yeah.
It's kind of like, you have those nice theoretical airspeeds and convex, but like, I guess in practice, empirically speaking, like in practice, how bad is the initial?
It's really not bad. You can 100% do it. Yeah. So I would say like, we're kind of cowboys to some extent. We just do it, right? And it's mostly fine. And if you're just doing this in the lab, it's fine. And people do it, right? And lots of people do that, right? Like lots of people do non-convex stuff online, and it's mostly fine. But if there's like human lives in the mix, like aviation kind of applications, autonomous driving applications to some extent, like when it's that kind of high stakes thing, you start to want to think harder about it. And I would say the convexity thing, it's like partly about this, but it's also tied up in the real time thing. Like if you really want to get an answer in 10 milliseconds, if you have a convex problem, you can guarantee that. You can say exactly how many floating point operations it will take to get an answer for a convex problem. And you can just like 100% like lock that down and know it will be hard real time. You can always solve it, right? Which is really, really nice thing. Whereas for a non-convex problem, like those are NP hard in general, and you can't say anything about getting a solution.
Are there like specific kind of like common failure modes, I guess, for the initial soft landing problem?
To be honest, like I haven't looked super hard at this. Like I don't think it's pretty benign. Like if you wanted to do this with the full dynamics, and just do nonlinear MPC, I'm pretty sure that would work pretty well, and you could do it, to be clear, right? But the kind of the thing here about it is like this has all the guarantees. You can say all the things about it you want to say, and it works really well. And you can solve what ends up being a pretty modest size SOCP at really high rates on it, like an embedded computer. The other piece of this is like that Mars example that's running on a RAD 750, which is a like state of the 1990s PowerPC G3 from like an old iMac, basically. Like the rad hard compute that like NASA has for these Mars things are like things from 25 years ago. Like they're really, really kind of crappy CPUs because they have to be radiation hardened. So your compute limits are really serious. I think the RAD 750s run at like 200 megahertz or something. It's like really, it's something from like basically what was in the old iMacs in the 90s is what those things are. So the compute limits are also a real thing. And like being able to do this where you, again, can guarantee a solution in a few Newton steps with an SOCP solver or whatever is also very, very nice.